So the next topic we're going to cover is to mine contextual and collective outliers. The contextual outliers, as we mentioned earlier, is the outlier that deviates from the majority of the objects within a context. So the idea is, if the context can be clearly defined, then we can transform it to a conventional outlier detection algorithm. For example, we can just only select the objects using this context. For example, temperature. We can find all the temperature, summer day temperature in Tucson, and mine outliers here. We can find, okay, 100 Fahrenheit is not outlier for a summer day in Tucson, but 150 Fahrenheit is. So which basically you use a subset of the data to mine outliers. The second, if the context itself contains very few customers, very few data points, then directly applying this method is going to be a little bit of a risky, because you don't have enough data to support any of the argument, whether one observation is normal, another is negative. So you can then use more advanced method to put more data points into this consideration. One example way of doing this is to, with the training example, learn a mixed model U. Again, this is EM. When you look at learn a mixed model, you should, the word EM should pop up in your mind, the expectation maximization algorithm. We first learn a model U on the contextual attributes, then we learn another mixed model V on the behavior attributes. Behavior attributes and contextual attributes, we defined it earlier. In this example, the temperature example, the behavior attribute is the temperature. The context attribute could be Tucson, summer. And then we can learn a mapping of this, giving this contextual, what's the probability for us to see this behavior. And then we can actually create, put this together and compute an outlier score. This formula may look like abstract and you couldn't make a lot of sense of it, but if we put it into our direct concrete example, it's going to be clear. So the score, the formula is this. If in this case we have Tucson winter, have a daily high temperature of this Fahrenheit, so our contextual attribute is going to be Tucson winter. Our behavior attribute is 110 Fahrenheit. Following this formula, we are actually going to compute this score as this. So probability of this observation occurred in winter has this degree times, given winter, we have this degree. So this is context, this is behavior, and times the other context. The other context is Tucson, and same thing. And we can compute a score. Compare this to, let's say, New York winter have a daily temperature of 110. You can see that this score, this probability is going to be greater than this probability. So therefore, this New York's observation is going to have a much more smaller outlier score. And this make it outlier. So SO, the smaller the SO, the greater the chance that observation is outlier. So I hope this example explains that formula in a more intuitive ways, that you compute the, that when you, after you learned the model, that you can actually precisely compute, more precisely estimate the probability for those values. However, in some applications, it's not very easy for us to clearly identify contextual, how much of the context should need to be taken into account. This example, if a customer suddenly purchased a product that's unrelated to those products that she recently browsed, it is not clear how many earlier browsed products need to be taken into consideration. So it's hard for us to define this context. In this case, we can model the normal behavior with respect to context. There are a number, so this becomes a prediction problem, like a classification problem. Given all those attributes, we use those attributes, contextual attributes, to predict the behavior attributes, the value of the behavior attributes. We use all of them. Typical algorithms that we use, because we're talking about, in this case, a sequence of things, then there's lots of sequential learning algorithms. Markov model is one, finite state machine is another. We can also use prediction, regression, if we predict the numerical values, if the behavior attribute is actually a numerical. So again, in this case, we converted the problem to a classification problem. Well, when we talk about classification problems, there has to be training examples and all that. Mining collective outliers, it's more challenging, as we mentioned earlier. Collective outlier occurs when the objects as a group deviates significantly from the entire data. So in order to detect those, we need to examine the structure of the data set. So in the example illustrated here, this can be easily identified using a density clustering algorithm. But a lot of cases that we do not know if our data presented like this. So we have to understand the structure of the data set first. So the collective outliers often are very application dependent. There is not a collective outlier detection algorithm that works for all of our collective outlier detections, because the structure of the underlying data is different. For example, there are 3 examples mentioned in the book: temporal data, time series and sequences, spatial data. For spatial data, we need to look at sub-areas, right? For temporal data, we need to look at the segments in the time, subsequences. For graph or network data, we explore subgraphs and see which of the subgraphs may be. A potential outlier. The collective outlier detection methods has 2 categories. One is to reduce the problem to conventional outlier detection. If we can identify structure list, then we treat every structure unit as one data object. For that object, because this data object represents multiple units, we need to extract the features for each of the objects, and then use conventional methods, other methods that we have learned so far. With this extraction step, we have converted a collective outlier problem into a global outlier problem or a contextual outlier problem. And then we can use the method that we discussed earlier to identify the outliers in those scenarios. And the second approach, which is much harder, is to model the expected behavior of the structure units directly. Here, depending on what for example, if you determine it's a temporal sequence, then you use Markov model because Markov model is good for sequence. Markov model can compute given observations and something that you want to predict. It will calculate a probability for a sequence to happen. So this using Markov model will allow you to compute a probability for this sequence to happen and see that's a rare case that you will not buy, I don't know, 10 hot dogs after you have eaten 5 hamburgers. And we mentioned collective outliers are very difficult to settle. And application dependent and computational cost is often higher.